Hello, in this video we're going to talk about another simple but important concept in rocketry, specifically model rocketry, and that is rocket stability. So this actually applies to all rockets, but there's three axes of motion that you could think of on any body, because we live in a 3D world. But for a rocket more specifically, you have a pitch axis, a roll axis, and a yaw axis. So this pen right here would be a good example of kind of the shape of a rocket. So pitch would be up and down like this, yaw would be like this, and then roll would be like this. Okay? So three directions of movement. But rockets, unlike this pen, are symmetric along the roll axis. Well, most rockets are. They're symmetrical all the way around. So if we took the cap off this pen, we would be fully symmetrical around the roll axis, but we're not symmetrical around the pitch axis, obviously, or the yaw axis. They are very similar, practically the same, because it is symmetrical around the roll axis. But if we cut this pen in half right here, it's obviously not symmetrical. Okay, so there's two more things we have to keep in mind. So here's our rocket right here. There's 2 points along the center line of the rocket. So pretend this is like a cross-sectional view of the rocket. There's two important values along that center line. That is xcg, or the position of the center of gravity, or xcp, which is the position of the center of pressure. Center of gravity, that is really easy to understand for most people. Most people are familiar with trying to balance something, on your finger, balance something anywhere. That would be your center of gravity. That is when so we have a rod right here. So the center of gravity would be right in the middle, because the mass on this side is the same as the mass on that side. But let's say we have a rod here, but we threw a mass on this side. Now the center of gravity moves this way, and it will be more right here. Now the mass on this side is the same as the mass on that side. And we're not going to get into how you can calculate it, but that makes sense. Pretty simple. Center of pressure, a little more confusing, a little more abstract of a concept, and that is where the center of the aerodynamic pressure is on that rocket as it flies through the air. So kind of a basic way to kind of calculate this, a basic theory of where the center of pressure would be, is at basically if you took a cross-sectional area of a rocket. So let's say you had a flat, so this would be like a side view, so your flat side. So if you took just like a tiny slice out of the center of a rocket, this would be the cross-sectional, this would be the side view, and then this would be the front view. It would look, just like, that would be a cone up here. It would look just like a rocket if you took the cross-sectional view, but we're neglecting mass of the rocket. So we don't care about where the payload mass is, we don't care about where the rocket, or the, any of the other loads in the mass, or loads in the rocket, so like where the rocket engine is, where the propellant is. We don't care about that. We're just looking at the cross-sectional area. So the center pressure is going to be where now the areas are the same. So like for this rocket here, the area of this shaded area is the same as the area of this shaded area. So this is where the center of pressure would be. So that's why model rockets have fins, because they provide stability when there's no like gimbal on the engine. So it provides stability. That's why we put fins on the rockets on the bottom. Okay. If we put the fins up here, up on the top, that would bring our center pressure way up to the top, and that's not what we want, because as we can see in this photo, for stability we want the center of gravity to be above, so more towards the top than the center of pressure. We want the center of pressure to be below the center of gravity. Now this can be measured, kind of a conventional way of measuring this is called a caliber. So if we had a rocket here, so let's say the distance, the diameter of the rocket, let's say it would be 10, say, centimeters. If the distance between the center of gravity and the center of the pressure was 10 centimeters, we would say that that is 1 caliber distance between the center of gravity and the center of pressure. Alright, so why do we want the center of pressure to be below the center of gravity? Well, first, to illustrate this, take a rocket right here. And this is going straight up in the air, and it is flying in the air perfectly straight, and it is flying, there's no wind gusts anywhere. The only wind is just coming perfectly symmetrical, prevailing, just on top of, everything's symmetrical, okay? So what are the forces at play here? We have the force of thrust. We also have the force of gravity acting on the center of gravity of the rocket. And we have our kind of pressure forces on each side of the rocket. But because everything's symmetrical, the wind's symmetrical and all that, the forces of pressure on both sides are the same, and ultimately this rocket will fly straight up in the air. Obviously, we don't live in a perfect world like this. We deal with wind, we deal with other factors. And so, let's say there was a disturbance, so let's say a wind gust or something of that nature, to come out of the left here. So, what might happen? Or let's say we had a disturbance that caused the rocket to tilt to the right. Okay? Any disturbance, now the rocket is pointing like this. So now, let's look at our balance of forces. Okay, our center of gravity, right? So we have our force due to gravity here. But now, as you can see, is no longer going straight back through this symmetric axis going straight through the rocket. So now it is now tilted. So the rocket, using the right hand rule here, is going to want to tip the rocket. So the force of gravity, if the rocket is now pointing like this, is going to continue to want to tip it that way. Okay, but that's not what we want, because that will cause our rocket to go unstable. But now, because our rocket's tipped this way, we have more prevailing wind coming on this side, or airflow, okay, coming down on this side. So therefore, our force at the center of pressure is going to be larger on this side. This might be easier to illustrate like this. We have a large arrow here, and now a small arrow going like this, because this area is kind of blocked off from the prevailing air. So now the force on this side is now stronger than this side. So what that's going to happen is that we have the force due to gravity pulling the rocket down this way, but now we have the force from the air pressure now wanting to tilt the rocket back this way, because it is rotating around kind of this point here, rotating around the center of gravity, so it will rotate it back. And then we have the thrust here. Now that is always acting straight through the axis of symmetry, so that won't really have an effect. Okay, so now let's go to this scenario where we have the center of gravity now below the center of pressure. So now we have that same disturbance that caused our rocket to tilt this way. So now we have our force due to gravity pulling this down. And now, again, we have our now prevailing wind right here, prevailing air, pushing down here. So the center of pressure force over here is going to be greater. But as we can see here, that is going to want to push the rocket, continue pushing it to the right, which will cause it to go unstable. So that's why we want the center of gravity, center pressure to be below the center of gravity. Now there's a concept called weathercocking. And this is similar to how like a weather vane works. So let's say we have a rocket right here. And so this phenomenon is that if the center of pressure is a lot farther from the center of gravity, so we have, let's say our center of gravity is up here, we have our center of pressure way down here. So this distance is now very long. So now the moment arm that's going to be pushing is now great. So if you have a wind gust here, the wind, so what happens here, let's go back to here. So this prevailing wind, obviously for a rocket, this kind of prevailing wind up here is going to be a lot stronger than, let's say, a wind gust. Because wind gust, let's say, is flying at 20 miles per hour. The rocket, on the other hand, is flying at, hundreds of miles per hour, hopefully. But so the force being, so we have a wind gust here, which pushes the rocket this way because it's going to act along the center pressure. But it's now that moment arm is going to be stronger than this wind right here that is wanting to push it back. Okay, so now the center pressure on this side is going to be a lot higher. This force is higher going this way, so it's going to start tilting in the wind and then fly into the wind, which is not what we want. So ideally, when we're designing a rocket, we don't want that center of gravity and the center of pressure to be too far apart, because now we have too strong of moment arms here that if the wind acts on the center of pressure, it's going to cause the rocket to go into the wind, and that's the direction we don't want it to go. We want it to go straight up. So we usually want the center of gravity and the center of pressure distance to be like 1, 2, 3 standard margins, which is caliber. So we don't want this distance to be too great comparative to the diameter of the rocket. We also don't want it too close together or obviously in the wrong direction.